Hello everyone. In this video, we are going to talk about binary search. Before I start the video, I would like to mention something. The purpose of this video is not to tell you about binary search or provide you with an implementation of binary search. The motive behind the video is to bring out clarity in binary search and build an intuition on how to use and when to use binary search. I'll be using a problem statement to teach binary search instead of teaching it as a method. Given a sorted array of distinct integers, let's call it nums, and an integer, call it target, you have to return the index of target in nums if target is present in nums, else return -1. In other words, return the index of a given element in the array. If the element is not present, you can return -1. So here's the example. So we have our nums array as 22, -22, -10, -2, 0, 12, 32, 34 and 199, and the target element is 34. Your output should be 6. We have another example where nums is 12, 15, 33 and 53, and the target is 21. Your output should be -1 since 21 is not present in the above array. So let's say that you have just learned your first programming language, or you are just starting your journey on data structures and algorithm. You only know about arrays, you don't know anything about binary search. How would you solve this problem? Yes, very simple. You would simply run a for loop over the array, and if you find the target element, you will return that index. So here's a quick Java implementation of that method. So this find index method will run a for loop over the array. In each iteration, it will compare the target with the current index value and return the index if the target is equal to the current element. If we are not able to find the element in the array, we will return -1. Well, this is good, but what is the complexity of this solution? So in the worst case, we might have to traverse the complete array because the target could be the last element as well, or the target might not even be present in the array, so we might have to travel the complete array. In that case, we will have to compare the target with each element of the array, which means we will have to perform n comparisons. So the complexity of this solution is O of n. So now the question is there some more information given in the question that we haven't used so far? Yes, the information given is that the array is sorted. This find index method would work even if the array was not sorted. But this additional information can be used to reduce the time complexity of our solution. So before using it, let's understand what sorted means. So if you are given that the array is sorted, it means that for every element in the array, let's call it current element, any number smaller than the current element can only be present to the left of current element, and any number greater than current element can only be present to the right of current element. For example, in our sample array, if we take -2, any number smaller than -2 can be present only to the left of -2, and any number greater than -2 can be present only to the right of -2. This means if we compare our target with any element in the array, we can reduce our search space to left side of that element or to right side of that element. Generalizing this, if we compare our target with the ith element, we can reduce our search space to maximum of i-1, n-i-1. I-1 is the size of left side of the current element, and n-i-1 is the number of elements to the right of the current element. Great. So we want to get the lowest possible value of this reduced search space, correct? So the minimum value that you can get on dividing the array into two parts is n/2. So by using one comparison, we can reduce our search space to n/2. Now since the n/2 size new search space is also sorted, and we can repeat this process, we can reduce the search space to n/4 by doing another comparison. Just compare the target with the middle element of the newly found search space, and then you will get a new search space of size n/4. We can keep repeating this process. What will be our terminating condition? We can repeat until our search space is reduced to size 1. when it is reducing, it has reduced to size 1, we know that either target is equal to this element or target is not present in the array. Therefore, we can return the answer accordingly. I know this is good in theory, but let's try run an example. So we have a search space of this initial complete array and our target is 34. Now since the number of elements in the search space is 8, which is even, there will be 2 middle elements. Let's decide that we will always take the left one of the middle element. We can take any of them, but let's decide we will always take the left one of the middle element. So we will compare our target with 0. Now since the target is greater than 0, 34 is greater than 0, we know that 34 can be present only to the right of 0. Therefore our new search space will become this. Now again we will find the middle element. Middle elements are 32 and 34. We will check the left one, which is 32, and again 34 is greater than 32, which means 34 can only lie to the right of 32. Sorry, space will become this. Now since there are 2 elements, both of them are middle elements, and we will take the left one, which is 34, and since 34 is equal to our target, we will return the index of 34, which is 6. So I think the algorithm is clear to you now. We reduced the search space from n to n by 2 by doing one comparison. We reduced the search space from n by 2 to n by 4 by doing the second comparison. So by doing k comparisons, we can reduce the search space to n by 2 to the power k. And in the worst case, what we want to do is we want to reduce the search space to one element. So that means n upon 2 to the power k is equal to 1. That is, n is equal to 2 to the power k, which implies k is equal to log n, where k was our number of comparisons. So in the worst case, we will have to do only log n comparison. Therefore, the time complexity of this solution is O of log n. So this technique of searching is called binary search. So binary search is nothing but another way of searching an element which works in case of sorted array. I hope I was able to make binary search a little more clear to you and have built a little more intuition about binary search in you. So I would recommend that you can pause the video here, look at the steps, and then implement it yourself. It is very, very easy. So the algorithm steps are: to maintain the search space, we will initialize 2 variables. One is start, denoting the starting index of the current search space, and another one is end, denoting the last index of the current search space. Then while the search space size is greater than or equal to 1, what we will do is we will take out the middle element. We will compare the middle element with the target. If the target is equal to middle element, we will return the index of middle element. If the target is less than middle element, we will update the search space by updating the n to middle index minus 1. Why are we doing this? Because we know that the target can only lie to the left of middle element. So we will say the last index of our search space is middle element minus 1. If the target is greater than middle element, we will update the search space by updating the start to middle index plus 1. Now the first index of our search space would be to the right of middle index. And if after reaching a search space of 1, we were not able to find the target in our array, it means that the target is not present in the array, and we will return minus 1. So I think you can implement it, but I'll provide you with an implementation as well. So this is a Java implementation. So we have initialized 2 variables, start and end, and initial values as 0 and length of nums minus 1. That is the last index of our search space and the first index of our search space. So while the search space size is greater than equal to 1, which means the start is less than equal to end, because our search space size would be end index minus start index plus 1. We will do is we will find the middle index, which is start plus end by 2. If target is equal to middle index, value at middle index, we will return middle index. If target is less than the value at middle index, we will update n to mid minus 1. If the target is greater than value at middle index, we will update start to mid plus 1. And if we were not able to find the target in the array, then we will return -1. So that's iterative implementation. You can also do a recursive implementation. I can provide with one in the comments, but I think you should be easily able to implement recursive one as well. I personally prefer the iterative, at least for binary search. So that's all for this video. I hope you enjoyed the video.